So what we'd like to learn how to do today is figure out how stable is your nucleus. The big key to nuclear energy and other nuclear things is figuring out how much energy we can get from our nucleus. So the nucleus we're going to do is going to be helium-4. So you know that helium-4 is composed of 2 protons and 2 neutrons for a total of 4 particles. So what you do is you start by looking at the particles before they form the helium. Okay, so we have 2 protons and 2 neutrons. So what we do is we get the mass of a neutron and the mass of a proton. Notice hydrogen 1 is simply a proton. So you're going to just use the mass of hydrogen 1 anytime you need a proton. You're going to use this anytime you need the mass of a neutron. Okay, so we're going to jump ahead and you get the mass of your original particles. So we have 2 protons and 2 neutrons. So it's going to be 2 times 1.0, and again, you check back here. A proton is 1.007825. And then 2 neutrons. Make sure you don't round. I know you want to round these, but you can't round them. Multiply it out and get your total. Multiply this out and get your total. Then add up all of those masses. So whatever you get here, and I don't have access to a calculator, so you're going to have to figure this out. Okay? Again, don't round. Then next, you look at what it makes, and it's going to make helium-4. So get the mass of the helium-4. 4.002602. And then you find what's called the mass defect. What that represents is the difference between the particles before they made the atom and the mass after they made the atom. And I hope you realize at this point that the law of conservation of mass is no longer going to hold true. The mass is going to change. Mass is going to vanish from the universe when we put these particles together. So we get our mass defect by subtracting. This should be a pretty small number. Again, I don't have access to a calculator, so you're going to have to figure it out for me. And that difference in mass will be in atomic mass units. Okay, to find your binding energy, what you do next is you use an equation that I hope you've heard before. It's Einstein's equation. It's the equation that lets us know that mass and energy are interchangeable. So the law of conservation of mass is no longer going to hold true because mass can turn into energy and energy can turn into mass. So whatever mass you got, you have to turn it from AMU into kilograms and then plug it in as your delta M, the loss of mass from the universe. You multiply by the speed of light and you square it, and you will get your energy. That's called your binding energy. What that represents is the energy that came off of the atom when this nucleus was formed. In order to pull that nucleus apart, you would have to put this energy back into your system. So the bigger the binding energy, the harder it's going to be to pull that nucleus apart. Your energy is going to come out to a pretty small number, maybe e to the 19th or e to the 20th or e to the negative 18th, one of those small values. You then want to convert it from joules, which is going to come out into electron volts. And the conversion is 1 electron volt equals 1.602 e to the negative 19th joules. This will turn a really small number into a really big number. Then what you want to do is this number is going to be so big, divide it by 1,000,000. This will get you in mega electron volts. Okay? When you're done with your mega electron volts, you then divide by the number of particles, in this case, 4. Okay? When you're all done, that number will tell you how stable your nucleus. The bigger this binding energy per nucleon is, the more stable your nucleus. So I'm not going to go any farther. I'd like you to write out this whole process, take a picture of your notes, including your final answer, and I'll make sure that you did it right. Good luck.